The second law tells us which processes are spontaneous, but not in a form that is easy to use. The Clausius inequality contains the heat, and the heat depends on the path taken. And in its tidiest statement, the S is greater than or equal to 0 applies to an isolated system, which is not what sits on a laboratory bench. This chapter turns it into something practical, rearranging the Clausius inequality for the conditions we actually impose: a fixed temperature, together with either a fixed volume or a fixed pressure. This will require us to introduce two new state functions, the Helmholtz free energy A and the Gibbs free energy G. From them follows the fundamental equations, the Maxwell relations, which trades quantities that are hard to measure for quantities that are easy, and in the end, a quantitative handle on the yield of a chemical reaction. We begin by rearranging the Clausius inequality, which gives d bar q is less than or equal to T ds. Thus du equals to d bar q plus d bar w, which is less than or equal to T ds plus d bar w, equals to T ds minus px dv. Thus at constant entropy and volume, a spontaneous process decreases internal energy of the system, and the equality holds at equilibrium. This is neat, but not very useful, because it is quite difficult to keep entropy of the system constant in the lab. We now define the Helmholtz free energy as A equals to U minus Ts. Then we have dA is less than or equal to minus Px dV minus S dt. Thus at constant volume and temperature, we have dA at constant V and T is less than or equal to 0, where the equality holds for equilibrium. So if the system is at constant temperature, which is much easier than keeping the entropy constant, and volume, then a spontaneous process lowers the Helmholtz free energy. This is in fact a masked statement of the second law, since we used the Clausius inequality to derive this relation. It is also quite common to keep the pressure of the system constant. We now define the Gibbs free energy G as U plus PV minus Ts. Then following similar argument, we have dG is less than or equal to VdP minus SdT. Thus at constant pressure and temperature, we have dG/Pt less than or equal to 0, where the equality holds for equilibrium. This is a very useful condition indeed. Now consider for reversible process. We have du equals to Tds minus Pdv. This is known as the fundamental equation. Since du is an exact differential, we may also have du equals to partial u partial s at constant v ds plus partial u partial v at constant s dv. By comparing the coefficients of dv, we have p equals to minus partial u partial v at constant s, and t equals to partial u partial s at constant v. This relation is a compact expression relating temperature, which is a zeroth law concept, internal energy, a first law concept, and entropy, a second law concept, which is quite neat. Similarly, we have dH equals to Tds plus Vdp, and dA equals to minus Pdv minus SdT, and dG equals to Vdp minus SdT. Subtly, fundamental equations holds for non-reversible processes, since internal energy, enthalpy, and the free energies are state functions. But earlier, we had for these non-reversible spontaneous processes, it must be inequalities. This is because the early expression holds for non-reversible processes between two non-equilibrium states, whereas the fundamental equations holds for non-reversible processes between two equilibrium state points. For example, earlier equations applies to water below 0 Celsius. It spontaneously freezes, lowering its Gibbs energy at constant pressure and temperature. Fundamental equation does not apply in this case, since water is not in its equilibrium state below 0 Celsius. The equilibrium state is ice. Now we focus on Gibbs energy. Clearly, from comparing coefficients, we have V equals to partial G, partial P at constant T, and S equals to partial G, partial T at constant P. But G is a state function, so we'll have the symmetry in its second derivatives. Then we have a partial V, partial T at constant P, equals to partial S partial P at constant T. This is known as a Maxwell relation. So if we can measure how the volume changes if we change the temperature at constant pressure, which is easy to measure, we also directly know how entropy changes as we vary pressure at constant temperature, which would be hard to measure directly. Then similarly, from the fundamental equations of Helmholtz free energy, we have partial P partial T at constant V equals to partial S partial V at constant T. And we'll have two more Maxwell relations on the screen from enthalpy and internal energy. We now turn to pressure dependence of G. And for an ideal gas, we have G of P2 at T equals to G of P1 at T plus nRT log P2 over P1. Therefore, Gibbs energy increases as we increase pressure. Now we look at temperature dependence of Gibbs free energy, which is a negative entropy. However, there's a more convenient form. Consider the partial derivative of G over T with respect to T at constant P, which turns out to be minus H over T squared. This is known as Gibbs-Helmholtz relation. At the end, we consider a simple but important chemical reaction known as the Haber process, which converts hydrogen and nitrogen into ammonia. This process uses 2% of the total energy of the world and feeds 4 billion people, which is about half of the human population. So it is important that we do this reaction cheaply and efficiently. The symbol of a circle with a bar across it denotes the standard state, which means two things at once. 1. The substance is pure, and 2. The pressure of 1 bar, which is very, very close to the atmospheric pressure. The delta R denotes the total amount of this quantity on the right-hand side minus the total amount on the left-hand side, weighted by the stoichiometric coefficients. Then delta RH standard equals to 2 HM standard of ammonia minus 3 HM standard of H2 minus HM standard of N2, where the subscript M indicates a mole of this substance. And the stoichiometric coefficients is defined so that delta RH standard equals to the sum of all the chemical species J, mu J, HM standard. And notice that the stoichiometric coefficients is positive for the products and negative for the reactants. And we have a similar expression for Gibbs energy. We now define the equilibrium constant Kp as the product over J, Pj over P standard to the power of mu J at equilibrium. And for a gas phase chemical reaction, there's a well-known relation between the standard Gibbs free energy of the reaction and the equilibrium constant, which is delta Rg standard equals to minus RT log Kp. And substituting the equilibrium constant Gibbs energy relation into Gibbs-Helmholtz relation yields d log Kp over dt equals to delta Rh standard over RT squared, which is known as the Van't Hoff equation and gives us the equilibrium constant's temperature dependence. For example, the Harber process is exothermic, meaning that delta H standard is negative, Kp decreases if you increase temperature, i.e. it moves to the endothermic side, which is the side of hydrogen and nitrogen. This is in fact the Le Chatelier's principle, i.e. the system moves in an opposite direction in order to counteract the external disturbance. Thermodynamics puts this into a quantitative basis and allows us to calculate the exact equilibrium constant for a given temperature, thus predicting the yield. We started with a system described only by few microscopic variables, with 3 statements about it. The first law tells us which processes are allowed, those that conserve energy. The second law tells us which of the allowed processes actually happen, and in which direction. The third law sets the 0 point of the entropy scale, so that we can tabulate absolute entropies and not only the differences. Every other result in this series follows from these 3. The work of deriving those results is worth doing. It gave us an upper limit on the efficiency of any heat engine, even though we know nothing about how a particular engine is built. It also gave us the temperature dependence of an equilibrium constant, and therefore the yield of the Haber process, or any other chemical reaction, even though we know nothing about how the molecules actually react. In both cases, the question seems to require a detailed mechanism. In fact, it requires only a state function and a constraint. This is the strength of thermodynamics, and also its limit. At no point did we need a model of what matter is made of. This is why thermodynamics was already useful to engineers decades before scientists agreed that atoms exist. But there's a cost. Thermodynamics tells us what must happen, but not why it happens. It does not explain why the entropy increase or why heat capacity has a value it has. To answer such questions, we must count the microscopic states, and that is statistical mechanics. Thank you for watching.